Here in this video, we want to derive an expression for the displacement of a particle in simple harmonic motion. But we start initially assuming that that's an oscillatory motion. The later level will prove that it is a simple harmonic motion. Like what we have done in the previous video, we are taking a vertical projection of a uniform circular motion. So imagine a body is in a uniform circular motion with a radius r. Let that is in uniform circular motion in a anti-clockwise direction. Then I need to draw its vertical projection onto the y-axis. So this is x-axis, negative x-axis, positive y-axis, negative y-axis. This is an origin. So let the body is in vertical projection in uniform circular motion. Somewhere here is the body. So this is the position of the particle in uniform circular motion. But I need to draw vertical projection as we have taught in the other video, previous video. So where is this vertical projection? It is like this. It hit the y-axis somewhere. So that's where its vertical projection is, right? So if you consider that vertical projection is making an angle theta with the origin with x-axis. If this is theta, this angle also becomes theta. And as this is radius, this is also the same radius r. So I will name this point already named as O, this point I named as A, this point is named as B. Vertical projection from the origin on y-axis is at a certain distance. Let me call the distance as y. So we can see there's a right angle triangle O B A. This is the right angle triangle O B A. So in a right angle triangle, I can write sine theta opposite side by hypothesis. Opposite side is y, hypothesis is r. That implies y is equal to r sine theta, where r is the radius. But if you notice that r, this is that r, this is that r from here to here, is the maximum possible displacement of vertical projection. Your vertical projection cannot be more than the radius of that circle because you are drawing a vertical projection on the y-axis from the origin. So the maximum distance from the origin to y-axis is nothing but the radius of the circle, right? So what we can write is maximum displacement is A. Amplitude, we call it like amplitude, and we can represent that with as A. So that is R itself in our case because R is the maximum possible displacement. It cannot be more than this, as I told you. That implies Y can be written like A sine theta, where theta is the angular displacement. Theta is the angular displacement. What we can write further is regarding that angular displacement. We know angular velocity is defined in vertical circular motion as omega s d theta by dt, and if these values are large, I can write theta by t. That implies theta can be written as omega into t. T is the time after which that much of angular displacement is happened. Omega is the angular velocity. Theta is the angular displacement. So we can write theta equal to omega t. So what happens to our equation now? Y equal to A sine omega t. This is the expression for the displacement of a particle in simple harmonic motion. Right? So you can notice little carefully if you notice this is expressed in terms of a sine function. Why it is expressed in terms of a sine function is simply because sine is a kind of a function who varies in between -1 to +1. Similarly, cos also varies in between +1 to -1 in the other way. So these two functions are called harmonic functions which repeats between two regular intervals. So they're apt and suitable to express the oscillatory motion. That's why we always express this oscillatory motion in terms of sine and cos functions. And I want you to be little careful in saying this because sometimes I can draw a vertical projection onto the x-axis also. I need not draw vertical projection always onto the y-axis. Yeah, here I want to tell you what happens if you are not drawn the vertical projection onto the y-axis but to the x-axis. So consider a uniform circular motion. This is the body who is moving in a uniform circular motion in a anti-clockwise direction. I'll just redraw origin, x-axis, negative x-axis, y-axis, negative y-axis. So wherever the body is, this time I want to draw a vertical projection onto the x-axis itself, not onto the y-axis. So when it is at x, position of the body is x. Vertical projection onto the x-axis is at x itself. So when the body moves, comes to the y, its vertical projection comes to the origin. So when the body comes to y, vertical comes projection to the origin. When the body comes to x dash, again vertical projection is at x dash itself because x dash is on x axis. When the body comes to y dash, its vertical projection is back to origin. When the body goes to the x, its vertical projection is at x itself. So position of the body, position of the vertical projection. If you look at the vertical projection carefully, it moves from x to O, again to x dash, then back to O, back to x. So this is also an oscillatory motion. So vertical projection onto the x-axis as well as the y-axis, both are oscillatory motions. So what if you want to draw a vertical, if the particle is at a particular position and you draw a vertical projection onto the x-axis, then this becomes x. So in that case, when you try to study the displacement, you will get it as x equal to a cos omega t, because earlier you are talking about y, which is a opposite side, whereas now this is not an opposite side, rather it is a adjacent side. So I will get a cos omega t. So that's why I mean to say an oscillatory motion can be represented as both in sine function as well as a cos function. So be careful about it. Both are both are oscillatory motions. Of course, later they will become a simple harmonic motions, but not tan functions and cot functions, right? That's how we have to understand. Thank you for watching. Next video, we'll derive an expression for velocity and acceleration.